Welcome to the chemistry guide. Today's topic is bond polarity. Uneven sharing of electrons in a covalent bond create a slight positive charge on one atom and a slight negative charge on the other atom due to differences in their electron negativity or attraction for electrons. For example, if you take HCl, here chlorine atom attract electrons harder than hydrogen. So, chlorine becomes partially negative while hydrogen becomes partially positive. It is leading to a polar bond. If atoms share electrons equally, the bond is non-polar because of their equal electronegativity. For example, H2Cl2. See here, both chlorine atoms have same electronegativity, so it is non-polar. If the total electrons are attracted by one atom, it becomes an ionic bond. For example, NaCl. Next, non-polar covalent bond. Where atoms share electrons equally, they form non-polar covalent bond. For example, H2Cl2, O2 and N2. See here, two hydrogen atoms share their electrons equally and their electronegativity is also same. So, they are non-polar. If we take carbon dioxide, the attraction of electrons from the oxygen on the left is exactly balanced by the attraction from the oxygen on the right. The opposite forces or dipole moments are equal in strength and opposite in directions. So, they cancel out, making the overall molecule non-polar. Next, polar covalent bond. In polar covalent bond, unequal electrons sharing due to electron negativity differences. It creating partial positive and partial negative charges. For example, I consider H2O. Here, oxygen more electronegative than hydrogen atoms. So, oxygen pull the electrons stronger than hydrogens. So, oxygen get partially negative and these hydrogens are get partially positive. In case of NH3, here nitrogen atom is more electronegative than hydrogen atoms. So, nitrogen pull the electrons stronger than these hydrogens. So, nitrogen get partially negative charge and these hydrogens are get partially positive charges. A measure of uneven electron distribution or polarity in molecule arising from differences in electron negativity between bonded atoms. Formula of dipole moment is mu is equal to Q into R. Here mu stands for dipole moment, Q stands for magnitude of the separated charge or partial charge, partially positive or partially negative in coulombs. R stands for distance between the charges in meters. Here remember one thing, this direction in a vector from the negative charge to the positive charge. Units of dipole moment is SI units coulomb meter. Common unit debye. 1 debye is equal to 3.33564 into 10 power minus 30 coulomb meter. Next we will see dipole moment in polyatomic molecules. Here in a molecule it have more than 2 atoms are polyatomic molecules. See here, in molecules that have more than 2 atoms are polyatomic molecules. The total dipole moment depends on how all the bond dipole moments add together. Each polar bond has its own dipole moment. These dipole moments behave like arrows or vectors. The net dipole moment of the molecule is found by adding all these vectors or arrows. Dipole moment depends on the shape of the molecule, lone pairs on the central atom, and if bonds are polar, the molecule can be non-polar if their dipoles cancel each other. For example, I consider beryllium fluoride. Fluorine is more electronegative than beryllium. So each BeF bond has a dipole moment pointing towards the fluorine atom. Beryllium fluoride has a linear molecular geometry causing the two equal bond dipoles to point exactly opposite directions and completely cancel each other out, and there is no net molecular dipole moment. If I take SiF4, observe here, each SiF bond is polar because fluorine pulls electron more strongly than Si. SiF4 has a tetrahedral shape. All four SiF bonds are equal and symmetrically arranged. The dipole moment of all four bonds cancel each other, so overall dipole moment is equal to 0. Here we will see NH3 versus NF3. Both NH3 and NF3 has trigonal pyramidal shape, one lone pair on nitrogen atom, but directions of bond dipoles is different. If we take NH3, nitrogen is more electronegative than hydrogen. So, NH bond dipoles point towards nitrogen atom. The lone pair dipole on nitrogen is also in the same direction. All dipoles add together, result is high dipole moment. In case of NF3, fluorine is more electronegative than nitrogen. So, NF bond dipoles point towards fluorine atom. The lone pair dipole points in the opposite direction. Bond dipole and lone pair dipole cancel each other. Result is low dipole moment. Let's see the Fuzan's rule. Here, Fuzan's rule tells us how much covalent character is present in an ionic bond. Not all ionic bonds are 100% ionic. Some ionic compounds show partial covalent character. More polarization is equal to more covalent character. Here, what is polarization? When a cation pulls the electron cloud of an anion, it is called polarization. See here this is cation and this is anion. Cation pulls the electrons of anion, so this is polarized anion. See here, these are cations attracted the electron cloud of anions. Let's see the conditions of Fuzan's rule. Smaller cation has high charge density. It pulls electrons strongly. For example, lithium plus greater than sodium plus greater than potassium plus. Next point, high positive charge. It has stronger attraction. They have more covalent character. For example, Al plus 3 greater than Mg2 plus greater than Na plus. Large anion has loosely held electrons and they have more covalent character. Examples, I minus greater than, Br minus greater than, Cl minus greater than, F minus. Here iodine is large anion than bromine. Bromine is large anion than chlorine. chlorine is large anion than fluorine. This is the order. So remember this line, small and highly charged cation plus large anion is equal to more covalent character. So that's all for this video. These classes are useful for who are preparing for EAMCET, JEE and NEET. So subscribe the channel.